An example of method of sections. I have this member, this truss here, A, B, C, D, E, F, G, H. Look, I skip over I. That's very common in labeling in engineering because I and 1 can be confused. K, L, M. If I got into O, we also usually skip over O because it can look like a 0. But anyway, I have this truss here. We usually label all the nodes with letters. If you don't have all the letters labeled on a truss, then you label them yourself, right? So we have this here. It's got 1, 2, 3, 4, 5, 6 equal spaces, which means that here, plus that, plus that, plus that, plus that, plus that is 18. So if it's 18 total and there's 6 spaces, that means each one of those spaces is 3 feet. The truss height is 4 feet tall. It's got 3 different point loads applied, 1 at the bottom, 2 at the top, of 10 kips, 20 kips, 15 kips. And I want to find the members KL and D. I want to find those forces. So if I did method of joints, I'd be bouncing all over the place trying to get there eventually. Whereas if I use method of sections, I can get there very quickly. Step 1, decide which free body diagram to use. Solve for any needed reactions after that for that free body. Apply the equations of equilibrium to find the forces. So I'm going to cut right through here at AA. Why is that? Because that's going to give me KL and DL. It could even give me CD straight away. And which side am I going to keep? Because that's the cut. I need to decide which side I want to keep. Do I want to keep this side over here, which has a lot more members? The members count doesn't really matter that much, but it's got 3 extra forces on it. And that's terrible. I don't want to deal with that. It's also even got a horizontal force over here. Actually, that force right there is 0. You can tell by inspection since there's no X load applied. So, but regardless, this right-hand side is more complicated. If I kept this left-hand side, all I'm going to have is RA and the internal forces that are exposed by this cut at AA. So I'm going to keep the left-hand side. Now, I need to find the value of RA before I go straight to that free body, because as soon as I go to that free body and I've got more unknowns that are internal forces, RA, if I don't know it, then I'm never going to know it. So let me find it using the entire structure. So I'm saying overall structure, let's sum moments about G. Why about G and not about A? It's, well, I want to know RA. If I want to find the reaction at A, the one place I'm definitely not going to sum moments about is A. Okay, so get that out of your head. A lot of students like to sum moments about the point they want to find the value for. You're not going to find any forces that are acting through point A. So if I go over here to G, it's because I don't care about RGX and RGY. I will get RA. So how do I do that? I've got 15 kips acting 3 feet away from G, and then I've got 20 and 10. I'm putting them in parentheses here to do a little bit simpler math because they're both acting at 6 feet away. And then I have minus RA times 18 feet equal to 0. So that makes RA equal to 12.5 kips. And I put that on my free body, or at least my overall structure. And when I go to build my free body, I now have that information for it. So here is my free body that I'm going to use. I've kept the part that I'm keeping, including the geometry that's relevant. I need to give an angle for that. That's going to be on my next slide. That free body will have a little bit more information. So I guess I'm being a little bit negligent here. I'm not showing that angle of this member. But I'm showing my overall dimensions, 3 feet, 3 feet, 3 feet, 4 feet tall. All of my externally applied loads, which is this reaction right here. And then my internal force vectors that pop up. I give them all names because I don't know their values. So now we solve it. Here I do have that angle information. This is a 3 feet width and a 4 feet height, which makes that a 3, 4, 5 force triangle. So if I do sum of forces in the Y equal to 0, I have 12.5 kips. And look at this. This unknown here is the only member that has a Y component of force. It's going to be different for all these different types of trusses, but this is pretty true for this one. You can see here this was an obvious, easy choice to do sum of forces in the y. So I've got 12.5 kips minus 4 over 5 times FDL equal to 0. That gives me FDL is equal to 15.63 kips, and since it was positive, it means it was tension. So this member here is 15.63 kips of tension. I update my free body diagram with that information. And now I look at my free body diagram and say, what else do I need? I need FKL. I don't need FCD. If I do summation of forces in the X, I still have 2 unknowns. So what do I do? Do I use a different free body, or do I maybe get a little bit more clever? I'm going to say, let's use a moment equation. And not any moment equation. I want some moments right here about point D. And point D is not even on the free body anymore, but you can sum moments about any point in space. And this point right here makes a lot of sense because that member and that member, their forces act through it. So it's going to make my equation easier, and it's going to get rid of this unknown as well out of my equation. So if I do that, I sum moments about D. I'm going to have 12.5 kips times 9 feet, and that's a clockwise moment about D, so negative. And then I'm going to have minus FKL times 4 feet. It's minus because it is also a clockwise moment, which you're going to end up getting a negative sign for your answer. 28.13 kips, which means 28.13 kips of compression is what FKL equals. And those are the answers that I was looking for. I didn't have to find all of these member forces all in between. No, I went straight there with method of sections.